Welcome, everyone, to the Sandbox AQ webinar. We are here with a very illustrious guest, our friend and our colleague, Professor Daniela Rus. Daniela is a worldwide expert on AI. She leads the CSAIL lab at MIT. CSAIL has more than 1,700 faculty and students, including 800 PhD students. We'll hear all about CSAIL today as well, but we're here really to focus on Daniela's new book, The Mind's Mirror, subtitle, Risk and Reward in the Age of AI. And we're going to hopefully delve into both the risk and the reward. So Daniela, first, tell us what has been some of the reactions to the book, The Mind's Mirror, that surprised you, or interesting reactions from places that you didn't think were reading the book. Just let's start with that first, and then we'll delve into the content of the book.
Jack, thank you for this question. I wrote this book because I wanted to explain to the public what AI is, what it can do, and what we can expect from AI in the future. And I've been very interested in painting a picture of AI that is accessible, that is grounded in the state of the art, both in technology and in applications. And that also addresses how individuals, organizations, and the planet can benefit from AI.
So let's kick into the book. One of the most striking things as you open the book, you talk about some key human traits, and then we'll talk about how AI comes into play here. You start with a key list of very, very human qualities: speed, knowledge, insight, creativity, foresight, mastery, and empathy. We don't have time to go into all of them, but let's start with insight. Insight is something that we always think of as a very human trait. Let's talk about that. You give some examples. For example, Hode Lipson, a faculty member that we both know, was testing out the idea of AI coming up and proving some physics equations. Tell us about insight, in your opinion, with how AI approaches insight and what we learned from Hode's examples as well.
So the reason I started with this list of powers is because we all want to improve. And with AI, we can all get better at all of these powers. Now, with respect to insight, it's actually really interesting. The story of Hode Lipson is really great. I love his research. And so he is interested in hypothesis generation. He is interested in using AI for new scientific discovery. And so he built an AI model that has some facts in it and some basic math in it. And he's wondering whether this AI model can crunch through vast amounts of data to figure out new truths about the world. And so he got a bunch of data from CERN, and he used this data to see whether he could come up with a new fundamental equation about how the universe works. So his system crunched and crunched and eventually came up with an equation. He went to the physicist friends and said, "Look what I found out." And the physicist said, "Oh, but we knew this already." But Hode was excited because even though the physicist knew already, he didn't, and his system didn't. So that was a kind of a proof that with AI, you can generate interesting new scientific facts or interesting new scientific hypotheses.
But talk to us about, there's some speculation, some discussions in the AI community around, yes, the neural network approach, the distributed network approach, obviously very powerful, particularly the transformer architecture, extremely, extremely effective and impactful. What do you think about the possibility of adding a bit of symbolic rational checking so that we could, one, maybe minimize some of the hallucinations and also bring the output of neural networks a bit more in line with what we see in humans, where, yes, we have the ability to do these kind of creative things, but also we do check against some rational principles sometimes. Go ahead, please.
Let's start by talking about transformers. Transformers are a very powerful technology. This technology works purely on statistics and on memorization. Transformers are what we call in the AI literature feed-forward networks. That means you feed some information into them, and there is a really complex process that organizes and sort of memorizes this information. And because of how information is organized as a result of massive training, we actually end up with being with stitching some part of the model here with some part of the model here when we generate answers. And this kind of statistical stitching yields unusual responses, which we equate with hallucination. And so, of course, there is a great interest in getting rid of hallucinations. And the technical community is working really hard on coming up with solutions. All of these solutions take some mathematical mechanism and then pass the result from the transformer through that mechanism in order to improve the chance that the result is correct. And this is fantastic. But I would say that equally exciting is to come up with new ideas about AI that also have the potential to perhaps go beyond what is achievable from memorization with feed-forward solutions. And one class of AI solutions that aims to tackle this new idea generation problem is called the state space model approach to AI. Now, in this approach, we introduce a new model for the artificial neural network, which is physics-based. Now, the transformer paper essentially says in the third sentence of the paper, we do away with convolutional neural networks and recurrences in order to enable parallelism and scalability. By doing away with recurrences, we essentially do away with feedback. And feedback is a very important aspect of intelligence and of learning. So this new class of models, state space models, bring back the notion of feedback through formulations that involve differential equations. So in my research group, we are studying two types of state space models. One is called liquid networks, and these liquid networks are inspired by the mathematics of the neurons of small species. And it has really wonderful properties, and it results in machine learning that is 1,000 times more efficient than a traditional transformer model for the same domain, for the same problem. We are also looking at using harmonic oscillators as another way of modeling the computation of the neuron. So basically, we change the computation of the neuron from the traditional model to this new model, which is essentially based on differential equations. We also change the function of the synapses, which are on-off computations in the traditional model. And we actually put differential equations on the synapses. And we change the wiring between the neurons to move away from feed-forward and allow for feedback. And so with these mechanisms, we are able to generate a new class of machine learning models that do not hallucinate by definition, by default.
So I think it's fair to say, Daniela, first of all, these are very exciting models, the state space models, and we're really just at the beginning. Yes, the Transformer paper, 2017, Attention is All You Need, was transformative, pun intended, but we're just at the beginning of a lot of innovation. And coming back to the book, coming back to insight, in that same chapter, you're talking about also deriving insight about ourselves, about our biometrics, about the kind of data that we collect in the so-called quantified self era that we're in now, with wearing Oura rings and all kinds of ways of getting that. You talk about sleep. Tell us more about that, with the kind of insight that humans have, but the kind of insight that maybe we can get from AI about ourselves and our health.
Well, Jack, it turns out that sleep holds a lot of secrets about our health and well-being. And since we're asleep, we're not really aware of what happens while we're out. It turns out that by studying sleep patterns, we can understand and we can detect well before doctors can whether we have an early stage of Parkinson's or of Alzheimer's. And this is very important because if we can detect these diseases at their incipient stage, we can act and we can administer medication. We can begin to make lifestyle modifications to ensure that the person's life is extended and the onset of detectable disease is delayed. And so there are many studies that are beginning to look into sleep and how our sleep actually is kind of like a magnifying glass into our state of well-being.
Thank you for those insights on insight. Let's actually now move to empathy. You have a chapter on empathy, which again, in many conversations about AI, people do not talk about empathy. So I think it's very refreshing. You included a chapter on this. And let's talk about both human and animal connections here. On the human side, we have micro expressions, of course, each of us in our facial communications. We have dozens of muscles that we can move in various ways, as I am now, to communicate these positive and negative and sad and happy communications and signals. Tell us about how AI, do you think, will interact and help interpret that and have a more empathetic relationship with humans?
Well, Jack, AI can really help us better understand the emotions of people surrounding us. So we all have micro expressions that are not detectable to the untrained naked eye. But with the use of AI, with the use of machine learning, these micro expressions can be detected. Again, we can also use the same idea of a magnifying glass to get insight into the activity of animals, our neighbors on this planet. And so in a research study in my group, together with some colleagues, we are looking into the language of sperm whales. Sperm whales communicate by clicking. They just go. And before we were able to use machine learning on audio recordings of whale sounds, we used traditional signal processing. And with traditional signal processing, it was possible to detect maybe 21 different phonemes that whales were able to generate. And that's because the water environment is so noisy. And when you record with a hydrophone in the water, you record the sound of the animal, but also the sound of the water and lots of other stuff. Well, with machine learning, you can kind of clean the signal. You can hear faint sounds that are indistinguishable from background noise in a more traditional model of processing the signal. And so we were able to show that instead of 21 phonemes, sperm whales have hundreds of them. And that means that their computational complexity is so much bigger than it was believed. We can also predict what sounds follow what other sounds. So we can predict that with short context and long context. We have no idea what they're saying, but it sure sounds like they're speaking according to some rules.
Let's go back now, Daniela. You referred before to earlier times, decades ago, where we didn't have the compute that we had today. And a number of experts back then came to a conclusion that took the field in a very odd direction. This and other inputs led to the first AI winter. And let's talk about that. What are some of the cautionary tales that we can take from this moment in science history? Danielle, take us through this. What happened? What do we learn from it? What do we do now in our current moment in 2024 when we, all of us think, oh, we have access to all information and all possibilities at all times now. But are we missing something? Are we blinded in the way that perhaps Minsky and Prepare also were back in 1969?
So the Perceptron book was a mathematical analysis of what is computable with single layer artificial neural networks called perceptrons. And what they showed is that mathematically, with this computational model, we can only represent linear functions. But if you have a linear function, you can simply create a deterministic algorithm. You do not need to go into the space of statistics and probabilistic outcomes. You can get something much better. And basically, like you said, that killed the funding in the field because people believed that this result actually addressed all neural networks. And so it's very interesting because at that time, the result was correct. But what was incorrect was the vision, the imagination we had to consider a world where we could have practically infinite data, practically infinite compute, and where scaling up to the levels at which we can scale today could really uncover the kind of fine patterns, the kind of fine insights that we are talking about and that I talk about in the book. And so an important lesson is that every instance of scientific discovery, every moment in time has some circumstances. But those circumstances could be so different 5, 10 years from now. And sometimes we're simply not capable of imagining that further in the future. And I will give you another example of this.
Please
And
do.
so let's go to the year 2000 when we had an incredible dot-com boom. We had such an extraordinary revolution in computing in the year 2000. But in the year 2000, nobody was talking about cloud computing. Nobody was talking about smartphones. Nobody was talking about social media. And yet, these three important technologies came online, came to us in the year 2007, only 7 years later. And they have transformed so much our society, how we work. They have transformed so much employment. There are so many jobs that people do today because we have these new technologies. These jobs include humanities. These jobs include scientists and also computer scientists.
Yeah, no, very, very good examples here and good caution for us going forward in terms of being open-minded and not closing key pathways off. So let's actually now turn to CSAIL itself, the very significant lab that you run at MIT. Talk to us about this interaction. How do you see it evolving, and how did this really come to this point where, in this particular field, we see so much interaction between academia and industry?
There has never been a more important moment for collaborations between academia and industry. The field is evolving very fast, and these partnerships are critical to ensure that the field is evolving in a way that is scientifically rigorous and that is world and business relevant. So what do I mean by this? Today's AI comes with a lot of technical challenges. We have data challenges, we have complexity challenges, we have security challenges, we have impact on climate challenges. All of these have to be tackled in fundamental ways. We have to improve our solutions. We have to get to the bottom of how these solutions make their decisions. Because if we do not understand, we cannot deploy them in safety critical applications. So collaborations between academia and industry have a very important role in defining and developing solutions to these technical problems. Academia also is less restrictive than industry, than companies in the way it moves forward. Academia is not restricted by any ROIs. And as a result, academia has the freedom to explore new kinds of ideas. And when those ideas bear fruit, the collaboration between companies and academia can then take those new solutions, those new types of insights, and deploy them, make them relevant today. So collaborations between companies who understand the needs and have the computation platforms and resources, and universities who can bring in the ideas that show what is coming around the corner, and bring in the talent who can actually take us along the path to see around the corner is very important.
Certainly, I think it's critical, particularly in a field like AI, where we need a lot of ideas to come from real world case studies, be it in medicine or be it in energy or be it in education, fields of education itself. It's great to have that collaboration. So, Daniela, just to wrap up, then, what is your wish list? I know many people out there, some may be listening to this webinar today, are worried about the future of AI, worried about the impact. What would you say, again, the subtitle of your book, Risk and Reward in the Age of AI? What are your concerns that you wanted to share, and how do you think we should address these concerns and look forward to a more positive impact of AI going ahead?
Well, Jack, there are a lot of risks with AI, because all the tools that empower the good people to get superpowers, as we discussed, also empower the supervillains. So these AI tools definitely have a dark side. And so the question is, how do we come up with a suite of guardrails that ensure that AI can be used for good, but that restrict the supervillains to get access to these extraordinary tools? And here we have the opportunity to develop some technical solutions to problems, but some of the problems are so sticky and complex that technical solutions will not solve them. So we really need to bring business policy and technologists together to figure out how we move forward. And this is really tricky, because in some sense we want to have the guardrails in place, but we do not want to stifle innovation. It's very important that we continue to innovate and develop our knowledge base. Studying AI is studying life, it's studying ourselves, is developing better tools for humanity and for the planet. And so if we have a low risk application, maybe it's okay for the tools to make mistakes from time to time. But if you have a safety critical application, maybe driving, then you cannot have mistakes. And so I think we need to figure out a set of rules and of testing regimens that fit the risk level of the application where they are being deployed. Now that we have identified and named this problem, we can really set out to come up with solutions at the intersection of technology, policy, and business.
It's been a pleasure to have this discussion with you today. I encourage listeners to this podcast to check out the book, The Mind's Mirror, Risk and Reward in the Age of AI, the new book from Professor Daniela Rus, head of CSAIL at MIT, and a great friend and colleague. Daniela, great to see you, and we'll see you very soon.
Jack, thank you so much. It's such a great pleasure and honor to be part of this conversation.